No more lithium. This all-new battery's miracle material will change everything in 2023. By the end of this video, you'll understand why the battery industry isn't replacing lithium. It's strategically diversifying around it, and you'll know exactly which chemistries are winning which market segments in 2026, so you can finally explain to your board why sodium-ion just captured 60% of stationary storage, while solid-state ceramics are dominating premium EVs. You'll walk away with the technical vocabulary and production timelines that separate insider knowledge from viral hype, including why mineral independence is the actual profit driver behind the $566 billion sodium-ion forecast. This is the roadmap the industry is already executing on, while everyone else is still arguing about lithium shortages. And what you're about to discover might completely change how you think about the future of energy storage. The lithium crisis that broke the industry. Here's what happened in 2025 that forced every major automaker to completely rethink their battery strategy. In late 2025, lithium carbonate Priam. The real problem was supply chain vulnerability. For decades, lithium extraction has been concentrated in just a few geographic regions. When maintenance shutdowns hit major production facilities in 2025, combined with surging demand from stationary storage installations, the entire electric vehicle industry found itself held hostage by what industry insiders started calling quote, white gold. BYD, one of the world's largest EV manufacturers, saw this crisis coming. In July 2025, they didn't just complain about lithium prices. They launched a 30-gigawatt-hour pilot production line in Xining, focused entirely on an alternative chemistry. A chemistry that would fundamentally change the economics of energy storage. And they weren't alone. But before we reveal what replaced lithium, you need to understand the problem that every battery engineer has been trying to solve for 40 years.
The impossible physics problem. There's a reason lithium dominated for so long, and it has everything to do with atomic physics. Lithium is the third lightest element in the periodic table. This isn't just a fun chemistry fact. It's the entire reason your smartphone, your laptop, and your electric vehicle exist in their current form. When you're trying to store energy in a battery, you're essentially moving ions back and forth between two electrodes. The lighter those ions are, the more energy you can pack into every kilogram of battery weight. This is called gravimetric energy density, and it's the holy grail of battery design. Lithium ions have a hydrated radius of just 2.76 angstroms. That tiny size means they can slip in and out of electrode materials quickly and efficiently. Now here's the problem that stumped researchers for decades. Sodium, the most obvious alternative to lithium, is the 11th element on the periodic table. Sodium ions have a hydrated radius of 3.58 angstroms, significantly larger than lithium. They're also 3 times heavier. For years, this meant sodium batteries were slower, bulkier, and stored less energy per kilogram than lithium batteries. Every research paper from 2015 to 2023 acknowledged sodium ion as promising, but not ready for prime time. So what changed? The breakthrough came from an unexpected place, and it wasn't a new chemical discovery. The hard carbon revolution. The material that solved the sodium problem has been hiding in plain sight since the 1990s, but nobody knew how to use it correctly until 2024. In lithium-ion batteries, the anode, the negative electrode, is made of highly ordered graphite. Graphite has a crystalline structure with perfectly aligned layers, and lithium ions slot between these layers in a process called intercalation. It's elegant, efficient, and proven. But when you try to use graphite with sodium ions, everything falls apart. The larger sodium ions can't fit between graphite layers efficiently. The battery becomes sluggish, unreliable, and impractical.
Enter hard carbon. Hard carbon is the opposite of graphite. Instead of orderly crystalline layers, hard carbon has a chaotic, low crystallinity structure filled with nanopores, tiny spaces that act like parking spots for sodium ions. Here's where it gets fascinating. Researchers at Tokyo University of Science and Novonix discovered that sodium ions don't just intercalate into hard carbon, they also aggregate into pseudo-metallic clusters inside the nanopores through a process called pore filling. And this pore filling mechanism is intrinsically faster than lithium intercalation into graphite. Let me repeat that, because it's critical. Sodium ions in hard carbon can move faster than lithium ions in graphite. This meant that the slow sodium narrative was completely wrong. The problem wasn't sodium, it was the electrode material. By 2026, hard carbon anodes had been optimized to the point where sodium-ion batteries could charge to 80% state of charge in just 15 to 18 minutes, compared to 30 to 45 minutes for standard lithium iron phosphate batteries. But charging speed was just the beginning. The real advantage of sodium-ion showed up in a place most people never think about. the minus 30-degree advantage. What happens when you try to charge a lithium battery in a Canadian winter? The answer is worse than you think. Lithium-ion batteries hate the cold. At minus 20 degrees Celsius, a standard lithium battery retains only 60 to 70% of its capacity. This isn't just inconvenient, it's a fundamental limitation that requires expensive engineering workarounds. Electric vehicles sold in cold climates need battery heating systems. These systems drain energy, add weight, and increase cost. Some Tesla owners in Norway have reported losing 40% of their range during winter months. Now compare that to sodium-ion. At minus 20 degrees Celsius, the 2026 generation of sodium-ion batteries retains 85 to 92% of their capacity. But here's the truly revolutionary part. Sodium-ion batteries can accept a charge even when the internal temperature of the cells is as low as minus 30 degrees Celsius.
You can plug in a frozen sodium-ion battery and it will start charging immediately. No preheating required, no energy wasted, no expensive thermal management system. CATL, the world's largest battery manufacturer, recognized this advantage and designed their entire Tianxing 2 battery series around it. On January 22, 2026, they launched the first mass-produced sodium-ion battery solution specifically for light commercial vehicles operating in diverse climates. Delivery vans in Sweden, micro trucks in northern China, city buses in Canada. The 45 kilowatt-hour sodium-ion pack became the default choice for urban logistics in cold climates almost overnight. But temperature performance was just one piece of the puzzle. The real question everyone was asking was, how much does this cost? The cost inversion that changed everything. In early 2025, sodium-ion batteries were more expensive than lithium. By mid-2026, the entire economics had flipped, and here's exactly how it happened. The battery industry faced what analysts called a cost inversion in early 2025. Despite cheaper raw materials, sodium-ion batteries cost more per kilowatt-hour than mature lithium iron phosphate cells. Why? Because manufacturing scale didn't exist yet. But by mid-2026, something remarkable happened. As gigafactories optimized their production lines for sodium chemistry, costs plummeted. And the cost reduction came from an unexpected source: aluminum foil. Let me explain. In lithium-ion batteries, you can't use aluminum foil for the anode current collector because lithium alloys with aluminum at low electrical potentials. This means manufacturers are forced to use expensive copper foil, which costs over $8,000 per metric ton. Sodium doesn't have this problem. Sodium-ion batteries can use aluminum foil for both the cathode and anode current collectors. Aluminum costs just $2,000 per metric ton. This single substitution reduced current collectors by nearly 50%. When you combine cheaper current collectors with abundant sodium carbonate and optimized manufacturing, the economics become undeniable. By mid-2026, at full industrial scale, sodium-ion battery materials were 20% to 40% cheaper than lithium counterparts. Pack prices for stationary storage in China dropped to $50 to $70 per kilowatt-hour, while lithium iron phosphate stationary storage converged around $70 per kilowatt-hour. The cost advantage was real, measurable, and growing. By the way, if you're finding this breakdown useful and want more content that cuts through the hype to show you what's actually happening in the tech industry, hit that subscribe button now. We're just getting to the most controversial part. But there was still one problem that threatened to derail the entire sodium revolution: the voltage curve nightmare. There's a technical detail that almost nobody talks about, but it's the reason why sodium ion will never fully replace lithium in certain applications. Lithium iron phosphate batteries have a flat voltage plateau. What does that mean? It means that as you discharge the battery from 100% to 20%, the voltage stays almost constant. For an electric vehicle motor controller, this is ideal. The power electronics can rely on a predictable voltage, and the car delivers consistent performance throughout the entire driving range. Sodium-ion batteries are different. Most sodium-ion batteries display a more linear voltage decay. As the battery discharges, the voltage drops steadily from full charge down to 0 volts. For an EV motor controller, this creates a serious problem. If the voltage drops too significantly as the battery depletes, the motor can't draw the necessary power. The result, the car feels sluggish toward the end of its range, even if the battery still has energy left. This is why researchers at Tokyo University of Science and Novonix have been obsessively focused on the pore filling mechanism in hard carbon.
By optimizing how sodium ions aggregate into pseudo-metallic clusters within nanopores, they're trying to create a more stable voltage plateau. Progress is being made, but the voltage curve remains sodium ions' Achilles heel for high-performance electric vehicles.
Quick question. Have you ever experienced your phone or laptop dying faster than the percentage indicator suggested? Comment yes if this has happened to you, because that's essentially the voltage curve problem we're talking about, just at a much larger scale. Which brings us to the strategic question that every automaker is asking right now, the market segmentation strategy. The battery industry in 2026 isn't about one chemistry winning, it's about each chemistry dominating specific market segments. Here's the actual breakdown. CATL, the company that produces more batteries than anyone else on Earth, isn't betting on sodium or lithium, they're betting on both. They call it the dual star strategy. Here's how it works. Lithium-ion batteries remain the choice for high-end passenger vehicles where range and performance are paramount. Sodium-ion batteries capture everything else: light commercial vehicles, urban delivery fleets, stationary grid storage, and backup power systems. The adoption pattern is following a clear hierarchy based on trade-offs between energy density and cost. For stationary storage, grid balancing, home energy systems, and industrial backup power, sodium-ion and flow batteries now hold over 60% of the market share. Why? Because physical footprint is secondary to life cycle cost and safety. You're not carrying the battery around, so weight doesn't matter. For light commercial and urban mobility, city buses, delivery vans, and microcars, sodium ion is displacing lithium iron phosphate. These vehicles operate on predictable routes with known range requirements. The low temperature resilience is vital, and the cost savings are undeniable. For high-end consumer and automotive applications, premium electric vehicles, mobile electronics, and performance cars, solid-state ceramic batteries and high-nickel lithium-ion cells remain dominant. Volumetric energy density is the primary constraint, and customers are willing to pay for it. This isn't a winner-take-all scenario, it's strategic diversification.
If you're starting to see why the one battery to rule them all narrative was always wrong, make sure you're subscribed, because we're about to reveal a technology that's even more advanced than sodium ion, and it's already shipping. But while sodium ion was solving the mass market problem, a completely different technology was being developed for the ultra-premium segment, the ceramic miracle from Prologium. At CES 2026, a company most people had never heard of unveiled a battery technology that addresses the two greatest weaknesses of conventional lithium-ion batteries, and it's already in production. Prologium isn't a household name, but in January 2026, they became the most talked about company in the battery industry. They unveiled the world's first mass-producible, superfluidized, all-inorganic solid-state lithium ceramic battery. That's a mouthful, so let me break down what makes this technology revolutionary. First, the electrolyte. Conventional lithium-ion batteries use a liquid electrolyte, a flammable organic solvent that carries ions between the electrodes. This liquid is the reason batteries can catch fire. It's the reason airlines restrict battery shipments. It's the reason electric vehicle fires make headlines. Prologium's battery replaces that flammable liquid with a superfluidized, all-inorganic solid-state lithium ceramic electrolyte and an all-ceramic separator. The result? A volumetric energy density of 860 watt-hours per liter, significantly higher than today's best liquid electrolyte cells. But energy density isn't the headline, safety is. Prologium's ceramic electrolyte is non-flammable and does not release combustible gases. But they didn't stop there. They integrated something called an active safety mechanism, or ASM. Under conditions of extreme temperature or voltage stress, the ASM releases materials that convert high-risk active components into stable crystalline structures. In other words, if the battery is damaged, it doesn't explode or catch fire. It chemically shuts itself down at the molecular level. Now let's talk about charging speed.
The ionic conductivity of Prologium's ceramic material is 57 millisiemens per centimeter at room temperature. That's roughly 5 times higher than standard liquid electrolytes or conventional sulfide-based solid-state electrolytes. What does that mean in practice? A Prologium battery can charge from 60% to 80% state of charge in just 4 to 6 minutes, compared to 20 to 45 minutes for liquid electrolyte lithium-ion. Here's a reality check. Would you pay 20% more for an electric car if it meant charging in 5 minutes instead of 30 minutes? Drop worth it or too expensive in the comments. I want to see where people actually stand on this trade-off. So who's actually using this technology right now? Where solid state is already deployed? This isn't vaporware. Solid-state ceramic batteries are already powering products you've heard of, and the list is growing fast. Prologium's technology is expanding into 4 key markets: luxury electric vehicles, humanoid robots, eVTOL aircraft, and AI data centers. For luxury EVs, the value proposition is simple: more range, faster charging, and absolute safety. When you're selling a $150,000 electric vehicle, the customer expects cutting-edge technology. Solid State delivers. For humanoid robots, weight and safety are non-negotiable. A robot working alongside humans in a factory or warehouse can't carry a battery that might catch fire if damaged. The high energy density means a longer operational time between charges. For eVTOL aircraft, electric vertical takeoff and landing vehicles, the combination of high energy density and intrinsic safety is the difference between regulatory approval and being grounded permanently. And for AI data centers, where thousands of GPUs generate enormous heat loads, fire risk is an existential concern. A battery backup system that physically cannot catch fire is worth the premium cost. This is where the market is segmenting: sodium-ion for mass market affordability, solid-state ceramics for applications where performance and safety justify the cost.
By the way, if you work in any of these industries, automotive, robotics, data centers, you need to be subscribed to this channel. We break down the technical shifts before they hit mainstream news. But there's a third category of batteries emerging in 2026 that most people don't even know exist yet: the tertiary chemistries nobody's talking about. While everyone debates sodium versus lithium, 3 alternative chemistries are quietly being deployed in extreme environments where conventional batteries simply don't work. Let's start with potassium ion. Potassium is even more abundant than sodium, and research at Dongguk University indicates that potassium-ion batteries can potentially offer higher energy densities than sodium-ion systems. The challenge right now is volume expansion. Potassium ions are large, and when they insert into electrode materials, they cause significant structural stress. But for long-duration grid storage, where you need to store massive amounts of energy for days or weeks, potassium ion is emerging as a serious contender. Commercial products are expected by the late 2020s. Next, zinc air batteries. In India, research by the CSIR and various IITs has led to zinc air batteries optimized for sub-zero temperatures. These made-in-India solutions are being deployed in remote mountain villages and military outposts in the Himalayas, places where lithium-ion batteries would fail to operate. Zinc batteries are inherently safer and greener than lithium, and some dual-function versions can produce hydrogen peroxide for water purification during the discharge process, providing a secondary utility for disaster relief and remote deployment. And then there's IBM's seawater battery. IBM Research has developed a battery chemistry that is completely free of heavy metals: no cobalt, no nickel, no manganese. Instead, it uses 3 proprietary materials that can be extracted from seawater. Think about the implications: no mining, no geopolitical supply chain risk, and no humanitarian concerns about cobalt extraction in conflict zones.
The seawater battery has demonstrated a power density of over 10,000 watts per liter and an energy density of 800 watt-hours per liter. It can charge to 80% in just 5 minutes. Right now, it's being tested for marine applications and offshore platforms, places where seawater is abundant and carbon-neutral harbor operations are becoming mandatory. Honest question: if you could power your phone by just dipping it in salt water, would that change how you think about battery anxiety? Comment game changer if that sounds like science fiction becoming reality. But perhaps the most unexpected breakthrough of 2026 has nothing to do with storing energy: the battery technology solving water pollution. Researchers discovered that the same electrochemical conditions that degrade batteries can be weaponized to destroy forever chemicals in drinking water, and it's already working. PFAS, per and polyfluoroalkyl substances, are called forever chemicals because they don't break down in the environment. They're in firefighting foam, non-stick cookware, water-resistant clothing, and unfortunately, drinking water supplies around the world. The carbon-fluorine bonds in PFAS molecules are some of the strongest bonds in chemistry. Nothing in nature can break them down. But researchers at the University of Chicago Pritzker School of Molecular Engineering discovered something remarkable: the electrochemical conditions that typically cause batteries to degrade can intentionally dismantle PFAS molecules. By using lithium metal, a common component in high-energy batteries, scientists created an aggressively reducing environment that attacks those carbon-fluorine bonds. This process achieves near-complete degradation, 94 to 95% of perfluorooctanic acid, or PFOA, one of the most persistent PFAS compounds.
And here's the breakthrough. It doesn't generate shorter-chain PFAS byproducts. It fully mineralizes the fluorine. This has led to the concept of a circular fluorine economy, where the fluoride recovered from remediated water is used as a raw material for manufacturing non-PFAS fluorinated compounds, such as pharmaceuticals and high-performance polymers. The battery industry, designed to power our future, is now helping to clean up our past.
If you made it this far and you're realizing this video is giving you information you won't find anywhere else, do me a favor and subscribe. The final section is going to tie everything together. So, what does all of this mean for you? The 2026 roadmap and what comes next. Here's the mental map you need to explain the battery industry to anyone who asks. The battery revolution of 2026 isn't about a single miracle material, it's about strategic diversification. Sodium-ion has captured 60% of the stationary storage market and is the default choice for light commercial vehicles in cold climates. It's cheaper, safer in extreme temperatures, and eliminates dependence on lithium supply chains. Solid-state ceramic batteries dominate the premium segment. Luxury EVs, humanoid robots, eVTOL aircraft, and AI data centers, where performance and safety justify the cost. Lithium-ion isn't dying, it's being reserved for applications where its superior gravimetric energy density remains essential. And tertiary chemistries, potassium, zinc, seawater, are filling niches in extreme environments and creating localized energy security. The global sodium-ion battery market was valued at $1.83 billion in 2025. By 2034, it's projected to exceed $7 billion. Some estimates suggest the full spectrum of sodium-ion applications could reach $566 billion by 2026 when you include grid-scale and industrial deployments. This is the roadmap. This is what's happening right now, while the headlines still argue about lithium shortages. The miracle isn't a single material. The miracle is the diversification itself, a fundamental shift from a resource-constrained past to an abundance-driven future. If this video gave you the clarity you needed to understand where the battery industry is actually heading, hit that subscribe button right now. Seriously, we're going deep on energy tech, AI infrastructure, and the technologies that are reshaping entire industries.
And here's my final question for you. Based on everything you just learned, which battery chemistry do you think will dominate by 2030? Comment either sodium, solid state, or something else. I genuinely want to see what you think after watching this. I read every comment, and your insights help shape what we cover next. Thanks for watching, and I'll see you in the next one.